Hello, today we're going to talk about intramolecular forces and potential energy. So let's review a little bit about covalent bonds. They're typically between two nonmetals, and they are sharing their valence electrons. Remember that they could be sharing them equally in a nonpolar bond or sharing them unequally in a polar bond. Covalent bonds, you can also have single, double, or triple bonds. Single, double, or triple. In a single bond, you're sharing 2 electrons. In a double bond, they're sharing 4 electrons. And in a triple bond, they're sharing 6 electrons between them. So as a result, if it's a single bond, this is going to be the longest of the 3 and the weakest of the 3. Whereas a triple bond is going to be the shortest because it's sharing the most electrons and the strongest. And of course, double bonds would be in between. So covalent bonding always happens at the lowest energy state. So this happens when the attraction between the nucleus of one atom and the electrons of the other atom is kind of balanced out by the repulsions. Okay, so this is kind of an interesting diagram. These are potential energy diagrams. I want you to think about the electrons being on the outside and the protons in the middle. And then you have 2 atoms, protons in the middle, electrons on the outside. The protons and electrons have to attract each other. Those are the attractive forces. But the electrons are repelling each other. And if they get close enough, the nuclei, the protons in the nucleus, repel each other. So those are the repulsive forces. And they have to find a balance there. So there's a perfect distance where that happens to form the bond. So on the x-axis here, this is always the distance between the atoms and between the nuclei. So that's what this image is showing you, how they measure the difference between the center of the atom. So in this particular one, it's 74 picometers. But whatever it happens to be, if it's, so this would be 0 distance here, that would be, they're right on top of each other, and that's not going to happen. It'd be super unstable. And then as they get farther and farther and farther apart. And eventually they would get so far apart that they're not even bound together again, so that doesn't work either. So there's like a happy medium. So that's for the x-axis. On the y-axis is potential energy. You want it to have the lowest energy state, so it's the most stable. So whichever distance makes it have the lowest energy, you'll see this like dip in the graph, and that minimum value there, that's the important one. All right, that's where it is the most stable at that particular distance. So let's talk for a second about bond energy. Bond energy is the energy required when breaking a bond. So this is something I really need you to remember. Breaking bonds is endothermic. Endo means the heat has to go in, or the energy has to go in. It requires energy to break the bonds apart. If you form a bond, if you form a new bond, that releases energy. And that's exothermic. Now, this should follow Coulomb's law for the most part. Always, you have to think about the size of the charge and the distance. So the stronger the attractions, or the stronger the bond, the more energy it will require to break those bonds. All right. So for example, a carbon-hydrogen bond has a bond energy of 413 kilojoules per mole. And the unit doesn't really matter for us in this, just as long as it's the same unit. And the difference there would be something like a carbon-nitrogen bond. A carbon-nitrogen single bond is 293. Well, nitrogen has a much larger radius than hydrogen, so it's a greater distance, so a weaker attraction, and therefore it requires less energy to break the carbon-nitrogen bond than to break the carbon-hydrogen bond. For another example, if we look at a carbon-carbon single bond, it's 348 kilojoules per mole versus a carbon-carbon double bond. carbon-carbon double bond is 614 kilojoules per mole. So when you're sharing more electrons, it increases the attraction, so it requires more energy to break that bond. So bond energies for ionic compounds, we just call that lattice energy, because an ionic compound will form a lattice. And what that will look like is you have alternating positive and negative ions in 3D space. I'm going to draw a 2D picture, but you just have to imagine that it continues the pattern in 3D. So that's your lattice, and lattice energy is the energy required to break apart the lattice. So very much the same as bond energy, just for ionic compounds in a lattice. And the greater the lattice energy, the stronger the attractions are. So greater the lattice energy, that means you know that there's stronger coulombic attractions. And of course, they're dependent on the same two things with Coulomb's law every time: the size of the charge and the distance. Yeah. So here's an example of a potential energy diagram. I didn't label my axes, but let's say this is your potential energy and then distance. So if I wanted to draw on here a carbon-carbon single bond, the single bond will have a greater distance because the single bond is longer, but it will also have a lower potential energy because of the bond energy required to break that apart. So you'll notice that that dip here is further to the right and higher up than it is for the carbon-carbon double bond. Let me label this carbon-carbon single bond. Now, for, let's use red, and we'll draw a triple bond. So the triple bond is the shortest, so its dip will be lower and further to the left than the other ones. So it's a shorter bond, but it's stronger as well, so it will have that lower potential energy there. And so let's go ahead and label that's carbon-carbon triple bond.